In our previous discussion, we have discussed instrumentation. So what is instrumentation? So it's determining or estimating a given sample, measuring some parameters such as conductance, potential, absorbance, or pKa is called as instrumentation, right? So now we are going to come to a new set of experiments, volumetric estimation. Volumetric estimation means what? We're going to give a sample and then we're going to determine the constituents, how much amount of constituents are present, right? So volumetric estimation is titration, it's a classical method. The same thing can be done by instrumentation. The first experiment in this volumetric estimation is total hardness. So total hardness, before going to how to do experiment and before we discuss what is total hardness, let us discuss or talk about what is hardness. What is hardness? So hardness, the first thing which comes in our mind is if the water does not, means hardness is related to water, isn't it? So today we are going to estimate total hardness present in the given sample of water. So why hardness is important? If water is hard, it does not give lather easily with soap. So if water is not giving lather easily with soap, it is called as hard water. And what do you mean by total hardness? That is what our answer I have told, that is a primary school answer, right? So what are the chemical components which cause hardness? Let us see today, and how to estimate it we will discuss today. Okay, so the components. Hardness is present due to presence of dissolved salts of calcium and magnesium. It might be carbonate, bicarbonate, sulfide, chloride salts of calcium and magnesium. If salts of calcium and magnesium is present in water, it causes hardness. So hardness does not give lather easily with soap. So there are two types of hardness, temporary hardness and permanent hardness. So temporary hardness is caused due to presence of bicarbonate and carbonate salts of calcium and magnesium, whereas permanent hardness is caused due to presence of salts like sulfate and chloride salts of calcium and magnesium. The permanent hardness can be removed by water. For example, if you are boiling water in a container, what happens in the same container daily? So the bottom of the water, the salts will be deposited, bottom and the sides of the container, right? That is hardness. The salts of calcium and bicarbonate salts will be removed. Okay, how to remove the permanent hardness? The permanent hardness can be removed by passing the water into quaternary ion exchange resins. Okay, by treating with resins. Okay, so now let us see how to estimate it. So we're going to take a sample of water and estimate it or titrate it against the EDTA taken in the burette using areochrome black to indicator. So when the color changes from wine red to clear blue color, we're going to note down the volume of EDTA consumed and we're going to calculate the total hardness present. So what is total hardness? The sum of temporary hardness and permanent hardness is called as total hardness. Okay, if you are measuring only the hardness caused by the salts of calcium and magnesium by chloride and sulfide, is called as permanent hardness. By carbonate and bicarbonate is called as temporary hardness. Combined together it is called as total hardness. Okay. Now EDTA. So what is EDTA? If any of your titrations, if you are using EDTA, that is called as complexometric titration. So EDTA is nothing but ethylene diamine tetraacetic acid. So ethylene, CH2 double bond CH2 is ethylene. So we're going to remove one bond there and we're going to put diamine. Diamine means two amine groups, NH2 groups. Okay, and then you're going to tetraacetic means four acetic acid groups. The two H2 groups which are attached to nitrogen are replaceable. We're going to attach the acetic acid groups. The EDTA, whatever is there, it is sparingly soluble. Therefore, sparingly soluble in water. So in order to make it completely soluble, we're going to use disodium salt of EDTA, and that is what it is. So the replaceable in this entire EDTA, only reaction is only H can be reacted, can be replaced. These things will not react. So two of the hydrogen will be replaced by sodium to give you disodium salt of EDTA. Okay. The part is, so any of your volumetric estimations will have two parts. First part is estimation, preparation of sand solution. Second part is estimation. Part 1. So preparation of sand solution. What do you mean by sand solution? So in none of our previous experiments we have discussed about standard solution, right? So we used to take all solutions in burette. That is never referred as standard solution. What is standard solution? So any volume, when you're preparing a solution, if weight of a solute and volume of a solvent is known, okay, weight of a solute and volume of solvent in which it is dissolved is known, we can calculate the exact strength. Strength means normality or molarity of the solution. That is called a standard solution. So we're going to take W grams of EDTA and we're going to add 1 test tube of ammonia. Why are we adding ammonia? Ammonia is added in order to increase the rate of dissolution. So the 1 gram of EDTA may take 1 minute to dissolve in absence of ammonia. But the same 1 gram of EDTA may take just 20 seconds in presence of ammonia. This is called increase the rate of dissolution. Okay. So estimation, in a bit we're going to take disodium EDTA solution. In conical flask 25 ml hard water we're going to pipette out. To that we're going to add buffer solution. The buffer used here is ammonium chloride. So indicator we're going to add a pinch of indicator erythrom black to indicate and titrate the sample of water against the titrant taken the burette until a color changes from wine red to clear blue. So ammonium monochloride buffer is added because buffer, what do you mean by buffer? Buffer which maintains the pH. So during the course of reaction, the H plus ions will be liberated in this solution. Okay. Since H plus is liberated, the pH will decrease. For the indicator to give this color, pH 10 is must. So in order to maintain constant pH, the buffer is added. Okay. So from the known volume of Na2EDTA consumed, total hardness of the given water sample is calculated. So there is a small demo of the experiment here. Let us see how to carry out the experiment. Estimation of total hardness of the given water sample using rapid titration method. So we will be using Na2EDTA here. So first we are going to prepare Na2EDTA. So we have Na2EDTA sample over here. This measured weight here. So first we are going to prepare the standard solution like this. 250 ml standard flask or weighing 250 ml standard flask or volumetric flask. So this we are going to add 1 test tube of ammonia. So ammonia is added in order to increase the dissolution of taken EDTA. So we are going to take the EDTA and add 1 test tube of ammonia. So then we are going to add little amount of water. So once you add Na2EDTA to this will be weighed again to know the amount of salt taken. So then we are going to add little amount of water to wash down the crystals into the volumetric flask. So once the crystals are washed down, we are going to dissolve the crystals. So let us swirl the bottle so that the crystals are completely dissolved. Okay, this is called as swirling. When the crystals are completely dissolved, we are going to add this distilled water up to the mark here and make up the solution up to the mark. So we are going to dissolve the crystals completely by swirling. This is called as swirling. Crystals are dissolved. So you can see the crystals are completely dissolved. So now we are going to add water up to the mark. Okay. So we are adding the water up to the mark over here. So once the water is added, we are going to shake it until we get uniform concentration. This is how we are going to shake it and release the pressure. Okay, again we are going to shake it, okay, and release the pressure. While shaking, it may leak. So even after leaking, the solution level has come down, we are not going to add any extra water. So water solution is prepared, we are going to transfer this into the 50 ml burette. Once it is transferred, we are going to pipette out 25 ml of the hard water sample. We are going to add 1 test tube of buffer and titrate. Pipette out 25 ml of hard water sample from the pipette. Okay, so we are going to add 1 test tube of buffer. So buffer is added in order to maintain pH. Okay, so we are going to add erythrom black indicator. So pinch of erythrom black indicator is added. We are going to add erythrom black indicator, pinch of it. Okay. You can see, right? We got wine red color. So this is sufficient. If you add more color, what happens is you cannot determine the end point. So determining the end point will become difficult. That's the reason we are going to add less indicator. So once you get this color, it's sufficient. So before adding, just see whether it is 0 or not. Okay, it should be 0. It's exactly 0. So I'm going to titrate it until we get light blue in color. So we need to titrate it until we get light blue in color. So add clockwise initially. So initially what happens when we add Na to EDTA, we get blue color in the middle and it disappears very soon. So near the end point, the blue color appears and it takes time to disappear. When it takes time to disappear, add clockwise. So you are supposed to control the knob in left hand, supposed to shake in, hold the conical flask and shake in right hand. With continuous shaking and the continuous addition, you will get the end point. So you got, so this is light blue color, this is the end point. When you get this end point, stop the experiment, remove the burette from burette stack, keep the burette to your eye level and note down the reading. It is around 13.6. So note down the reading as, final reading as 13.6 minus initial reading is 0, 13.6. Volume run down as 13.6.
Always initial reading should be 0 for each and every trial.
Concurrent balance. Okay. So we have got the complete titration and we got the end point as 13.1. The concurrent values was 13.1 and 13.0. So the concurrent value was 13.1. So the 1000 centimeter cube of 1 molar EDTA contains 100 grams of calcium carbonate. So for XCl centimeter cube, XCl centimeter cube means the volume of Na2EDTA rundown. The volume of Na2EDTA rundown was 13.1. So 13.1 centimeter cube or the normality molarity of EDTA was found to be 0.020 molar. So contains how much amount of calcium carbonate? So this cross multiply for 1 liter is 13.1 into 0.020 into 100 divided by 1000. So whatever we get here, it is for density. So if it is for 13.1 centimeter cube, it contains so much means we are supposed to calculate for 25 centimeter cube. Why? Because we have taken 25 centimeter, put it down 25 centimeter cube of hard water. So then 25 centimeter cube how much? So A into 10 to the power 6 divided by 25. So when you substitute here, it is 1048 ppm of calcium carbonate. So it is taken and it is measured in terms of calcium carbonate because it is easy, because the molecular weight of calcium carbonate is 100. Therefore, it is expressed in calcium carbonate so that it will be easy for calculation. Therefore, the total hardness is measured in terms of calcium carbonate and not other things. Okay, thank you.
Thank you.